Hello. So this is part 2 of Math and Astronomy. And where we ended at part 1, Tycho Brahe has passed away and he has passed along his data to his student, Johann Kepler. We also saw at the very end of the last one that John Napier is working on logarithms in England, and that's going to be very important as well. But let's move to the PowerPoint for this one and talk about the work of Kepler. So here's Johann Kepler. Kepler was a German mathematician and scientist living about the same time as a little bit after Copernicus and Brahe. And notice we're still in the northern part of Europe. So a lot of this work that's being done with this heliocentric model of the universe is in northern Europe, farther away from Rome and the fingers of the Roman Church. So the Roman Catholic Church. So Kepler has this data and he takes it and he starts looking for patterns. And Kepler was very much a Pythagorean. He believed that he was going to be able to find patterns, that he would see the geometry in it, that all of this must fit together some way so that what he could observe in the sky, the astronomy, could be interpreted mathematically. And that's very much what the Pythagoreans said. The Pythagoreans said it's all about number. Well, Kepler is saying, yeah, it is, and I'm going to show you how it is. And so here's what he did. He took that data and look at the years. I mean, we're talking around 1600 here. And he came up with 3 laws of planetary motion that were really, really important. The first law, the law of ellipses, says that the orbit of a planet is an ellipse with the sun at one focus. So he never, ever even questions the idea that the sun is at the center and everything else is going around. That's not a question. That's been established. But what he does find out is this idea of circular orbits, and Copernicus was into the circular orbits thing as well, but Kepler said, no, that's not it. Everything has an elliptical orbit. Some of them are more elliptical than others, but all of the orbits of all of the planets are ellipses, not circles. All right, so let's talk about that for a second. What's the deal with an ellipse? All right, so I've just got some notes here on an ellipse. This particular ellipse is centered at the origin 0, 0. And it's one of the conic sections. So think about if you've got an ice cream cone and you slice it this way, slice it at an angle so it goes all the way through from one side to the other side. The shape that you see when you look at that is an ellipse. And that's one way to define an ellipse. Another way to define it algebraically is that it is a set of points. And when you define it in that way we're talking about analytic geometry. So again, here's another example where this idea of the ellipse is going to be pushing mathematics, is pushing on what gets discovered and what gets studied in mathematics. And we've got Descartes right after this in analytic geometry. Okay, so back to the definition. In a circle, you've got a center. In an ellipse, you've got 2 points that are inside the ellipse, and they are called the foci, F-O-C-I. One of them is a foci, 2 of them are foci. And so one of them is a focus, 2 are foci. And so they're marked on the horizontal axis, F1 and F2. If a point is on the ellipse, and look at that point that's labeled X1, Y1, you look at the distance from that point to each of the foci, and you add those 2 distances together. And for every single point on that ellipse, the sum of those 2 distances is the same. Okay? Now think about how that's different from a circle. A circle, you've got 1 point and it's the center. For every point on that circle, the distance from the point to the center is the same. But this time on an ellipse, you've got 2 points. So you're measuring the distance from every point to these 2 points. You've got 2 distances. Add them together, you always get the same thing for your ellipse. So once you establish an ellipse, you've got the same distance, sum of the distances for all of those. So look down in the third quadrant, X2, Y2. The distance from that point to F1 is E1, and the distance from that point to F2 is E2. So since these are both points on the ellipse, D1 plus D2 would have to equal E1 plus E2. Here's the third point that's listed, that's given there. X3, Y3 is that far right-hand point, which is called one of the vertices. It's a vertex. So X3, Y3 is also a point on the ellipse. And if I look at the distance from X3, Y3 to the two foci, notice I've got to go all the way over to the farther one, F1, add that distance to the closer one, F2. That same distance, G1 plus G2, is the same thing as D1 plus D2, which is the same as E1 plus E2. All right, well, notice that G1 plus G2. Imagine you're going to take that G2 and you're going to pick it up and you're going to move it over here to the left of G1. Well, what you get is the length of that axis from vertex to vertex. That's called a major axis. That long part of it, that's the major axis, and then the minor axis is the short part. Now, of course, sometimes ellipses are long this way, sometimes they're long vertically. So either way, the length of a semi-major axis, we'll see that phrase in a little bit. A semi-major axis is half the length of the major axis. I said length of semi-major axis equals the length of the major axis. No, it doesn't. The length of the major axis is 1/2 the length of the major axis. Okay. All right. One more thing about an ellipse. When you look at the equation of an ellipse, or let's think about the equation of a circle, x squared plus y squared equals 1 is one example. 3x squared plus 3y squared equals 12. There's another one. I mean, all kinds of different examples. But what you've got with an equation of a circle is you've got an x squared term, you've got a y squared term. Same thing with an ellipse. You've got an x squared term, you've got a y squared term. But with a circle, the coefficients of those two terms are the same. If it's an ellipse, those two coefficients are going to be different. So that's how it's easy to spot the equations of them, which one's which, an ellipse or a circle. Neither one of those is going to yield a function. Both a circle and an ellipse fail that vertical line test. So neither one is a function, but they both have equations. Okay, let me go back. And I have to pause for a second. All right, so I'm back. We're at law number 2, law of equal area in equal time. Excuse me. The position vector pointing from the sun to the planet sweeps out equal areas in equal times. Okay, what exactly does that mean? Okay, let's move over here. Okay, here we go. So if I'm a planet that's moving around the sun, and the sun, by the way, is out of focus. I don't think I mentioned that a while ago. The sun is not in the center of the ellipse. The sun is at one of the foci. So the sun is at one of the foci. It's out of focus. And I'm a planet moving around there. Up there in the first quadrant, my planet moves from point A to point B. And when it talks about the vector that is swept out, it's talking about the vector from the sun to the planet at point A. And then as it moves to point B, that region that's swept out between A and B, I've got it shaded there. That's the area that we're talking about. That's the area that is swept out by the vector as the planet moves from point A to point B. Okay, well, it keeps going in its orbit. Planet comes over here to E and it moves to F. So as it moves from E to F, the planet is sweeping out another area, and it's that part over there. D2 is right next to it. It's that kind of fatter shaded area. Now what's going on here is that if the length of time that the planet takes to move from A to B is the same as it takes to move from E to F, those two areas are the same. The areas of those two regions that are swept out are going to be the same. And as the planet moves on around in its orbit, if it takes the same length of time to go from C to D as it does from E to F, the area that's swept out as it moves from C to D is exactly the same as it is when it moves from A to B or from E to F. All right, well, so what's the big deal about that? What that means is, think about it, compare E to F and A to B, okay? When the planet is moving from A to B, it's farther away from the focus in our picture. It's farther away from the focus than it is from E to F. It's farther away. That area is kind of long and skinny. E to F, it's fatter because that D2 is longer. The areas are the same. So the distance from A to B has to be less than the distance from E to F. In order for the sizes to match up, A to B has to be shorter than E to F. All right, but it takes the planet the same amount of time to move from A to B as it does from E to F. So where is it moving faster? Well, it's going a shorter distance from A to B than from E to F. So if it's the same length of time, it's going farther from E to F. It's got to go faster. So the planet's moving faster when it's closer to the sun. The closer a planet is to the sun in its orbit, the greater its speed in its orbit. And that makes sense if you think about those arcs on the ellipse. D1 has to be shorter than D2. But if it takes the planet the same amount of time to move from here to here as it does here to here, the velocities are different. That's what that second law is saying. Okay. And the consequence of that then is, number one, that the speed or the velocity of the planet throughout its orbit changes. That's really important. It's not always traveling at the same speed. Ptolemy realized there was something going on with that, and that's why he added that little spirally looking thing, that little circle in a circle. He knew that it appeared to be moving faster. He just didn't think it was. He just did this little spirally thing to take account of that, to make up for it. Okay. Kepler said, no. Planets are moving at different speeds within their orbits, and they're moving faster the closer they are to the sun. Okay. All right. Go back up to the third one. Third one's longer. It is absolutely certain and exact. I just love the way he says that. Kepler is very confident of his work. It is absolutely certain and exact that the ratio which exists between the periodic times of any two planets is precisely the ratio, not ration, ratio of the 3/2 power of the mean distance of the planet to the sun. All right, so he's setting up a proportion between two planets. He's looking at their periodic times. In other words, the time of their orbits. How long does it take them to go around the sun? And the mean distance of the planet to the sun. All right, well, that means that average distance. Remember, that distance is changing as that planet moves around in an ellipse. Where's that ellipse? The planet's moving around in an ellipse, so the distance to the sun is changing. So the mean distance is that average distance. And as it turns out, that average distance is half the length of the major axis. Okay. So let's see what that proportion would look like. Planet number 1, we're using 1 as our subscript. So the periodic time, the length of time for the orbit is P1. The mean distance to the sun, the average distance to the sun is D1. For planet number 2, the periodic time is P2, mean distance is D2. So he said the ratio of the periodic times. So P1 over P2. Okay, that's one ratio in my proportion. That's the left-hand side of the equation. He said the other side of the equation is the ratio of the mean distances raised to the 3/2 power. So that first equation you see there is the equation that represents that statement. Okay, well, let's examine that a little bit and look at the consequences of that. If I square both sides of this equation, I'll get the fraction on the left-hand side, P1 over P2 squared equals D1 over D2 to the 3rd power. And I'm just going to raise the numerator and the denominator to the powers that are there. That's what I get in this equation. P1 squared over P2 squared equals D1 to the 3rd over D2 to the 3rd. And that means that I can divide both sides of this equation by d1 to the third, multiply it by p2 to the second, and I end up with an equation where I've got information about one planet on one side and the other planet on the other. So for every single planet, we've got this ratio. Every single planet, the square of its orbit time over the cube of its mean distance is the same for every single planet. And in your homework, you've got a table with data that I got from the NASA website. It's got this information from different planets. And for Earth, we use 1. The periodic time for Earth is 1 year. So we're measuring the other planets, we're measuring compared to our year. So for Venus and Mercury, it's going to be less than 1. The periodic time is less than 1. Mars and the other planets, they're greater than 1. The mean distance to the sun is also in terms of Earth's distance. So the mean distance from the Earth to the sun is 1 astronomical unit. And then that mean distance to the sun for all the other planets is measured in terms of Earth's as the unit. So again, for Venus and Mars, for Venus and Mercury, that's going to be a number less than 1. For the other planets, it's going to be a number greater than 1. When you take those numbers, if you and by the way, for Earth, we've got the ratio of 1 squared to 1 cubed. So we get 1. What's that mean? When I put those numbers in for other planets, I should get 1. And that's what you're going to see when you look at those numbers and check that out. Okay. All right, so that's the end of the second module, or the second part of this. The third part, we get to Galileo. All right, see you there.